Your phone keyboard predicts pizza after you type, I want. Now imagine a system that does the same thing, but with 175 billion adjustable predictions, trained on the entire internet and capable of writing legal documents, debugging code, or tutoring you in quantum physics. That's an LLM. By the end of this, you'll understand how LLMs work from first principles, how text becomes numbers, how those numbers flow through a neural network, why it all works at scale, and the open mysteries that still have researchers puzzled. Before LLMs, AI was fragmented. One model for translation, another for sentiment, another for grammar checking. Each needed a human to hand-label thousands of examples. An LLM is different. One model learns from raw text alone and somehow acquires the ability to do hundreds of tasks without being explicitly trained on any of them. That's the revolution. Here's the genius move. LLMs don't memorize the internet, they compress it. A 1 terabyte dataset becomes 350 gigabytes of learned parameters. Like a JPEG compresses photos into lossy file, an LLM compresses text into statistical patterns. That's why they hallucinate. They're reconstructing likely patterns, not retrieving facts. An LLM is fundamentally simple. It predicts the next token, the next piece of text, based on everything before it. A token is a chunk of text, usually a word or part of a word. Tokenization is the first step. Your raw text gets sliced into these pieces using algorithms like byte pair encoding, creating a vocabulary of about 100,000 tokens. Why tokenization matters? It's the model's interface with reality. Poor tokenization makes things inefficient. Some languages are 10 times worse at tokenization than English, which means they cost more to run on an LLM. It's a permanent artifact, the one part of the pipeline that isn't learned. Next, each token becomes a list of numbers, a vector, 12,288 dimensions in GPT-3. These numbers represent meaning. Similar concepts cluster together geometrically. Feed enough tokens through the learning process, and word arithmetic emerges. King minus man plus woman approximately equals queen. That's the embedding space. Now the model needs to weigh which tokens matter for predicting the next one. Your phone keyboard ignores the when predicting pizza. It focuses on want. An LLM does this billions of times via self-attention. Each token asks, which other tokens do I need to understand me, and gets a weighted answer. This is the core innovation that made transformers powerful. Technically, for each token, the model creates 3 views. A query, what am I looking for? Keys, what do I contain? And values, what information do I give if matched? The query dot products against all keys gets scaled and softmaxed to a probability distribution, then uses those weights to pull the values. This happens for every token in parallel. Why this design? Attention is parallelizable. All tokens see all other tokens in one operation. Old models used RNNs, which processed token by token sequentially. Attention is O of n squared with context length, but parallelizable. RNNs were O of n, but sequential, and they'd lose information over long documents. The model doesn't run attention once, it runs it 96 times in parallel, each head learning different relationships. One head tracks pronouns, another verb-subject agreement, another syntactic dependencies. Multiple perspectives on the same data. The outputs concatenate and project back. This is multi-head attention. After attention, each token gets processed by a feed-forward network, 2 neural network layers with the inner layer 4 times larger. This layer doesn't mix information between positions. Instead, it acts as key value memory. Research shows FFN layers store factual associations. They're where Paris is the capital of France lives as a learned pattern. These attention and feed-forward blocks stack 96 times. Without safeguards, gradients would vanish in deep networks. The model uses residual connections, shortcuts, plus layer normalization to stabilize training. Every layer adds to the prior layer rather than replacing it. This is how you train a 100-layer network at scale. Finally, the model applies a mask during attention. During training, it can only look backwards. Token 5 can see tokens 1 through 5, but not 6 onward. This enforces autoregressive generation. Predict the next token using only the past. Without this constraint, the model would just attend to the answer itself and cheat. After the transformer stack, the model projects to logits, raw scores for all 100,000 vocabulary tokens. A softmax converts these to probabilities. During training, the loss is how surprised the model was by the actual next token, optimized to minimize this surprisal across terabytes of text. That's pre-training. Pre-training teaches the model language from raw text alone. Billions of examples. Supervised fine-tuning adds high-quality human demonstrations. Here's how to answer questions. Here's how to help. Then reinforcement learning from human feedback. Humans rank model outputs, a reward model learns preferences, and the LLM optimizes to please the reward model. At inference time, one clever trick, the KV cache. When generating token 100, the model needs key value vectors from tokens 1 through 99. Recomputing them is expensive. Instead, cache them from previous steps. Each new token is computed fresh, but it reuses cached history. This keeps generation practical despite quadratic attention. Training scales this to frontier size. Thousands of GPUs running for months. GPT-3 took 3.14 times 10 to the 23 floating point operations. LLM 270 billion ran 1.7 million GPU hours. GPT-4 took an estimated $100 billion and thousands of A100s. Scale is the strategy. Context windows, the amount of paths the model can see, have grown from 2048 tokens in GPT-3 to 1 million plus in Gemini. But attention is O(n) squared. Doubling context quadruples compute. This scaling law drives research into linear attention and state space models. It's the fundamental barrier to infinitely long context. Emergence. At 6 billion parameters, a model can't do three-digit addition. At 13 billion, it can. These capabilities don't gradually appear, they phase transition suddenly at scale thresholds. Reasoning, in-context learning, and arithmetic all emerge unpredictably. We don't program these abilities, scale manufactures them. Scaling laws are predictably predictable. Model loss depends on only two variables, parameter count and data size. You can forecast GPT-4's accuracy before training it using two variable power laws. This is one of the most reliable empirical laws in AI. Bigger plus better data equals better every time. But mysteries remain. Why do models hallucinate, confabulate false information with confidence? Is reasoning true computation or just pattern matching at scale? We can't interpret the 175 billion dimensional knowledge graph. High-quality text is running out. And can models fake alignment, appearing helpful during training while hiding their true goals? LLMs are already reshaping software engineering, knowledge work, and education. They generate code, audit code, explain complex systems, and tutor students. But they're not AGI. They're compressed statistical models that reconstruct likely patterns. Powerful, but limited. And the biggest question, how far does this architecture scale? Scaling is just the beginning of the story. If you want to master the architecture of intelligence and stay on the bleeding edge of AI engineering, make sure to like, subscribe, and hit the bell icon to catch every deep dive. Let's build the future one token at a time. Thanks for watching.